3.2 is on polynomial functions and their graphs. So what's going to happen in this lesson is we're going to learn a lot of different ideas about polynomial functions, and then we're going to put all those things together to be able to graph them. So let's start off with the definition of a polynomial function. So it's right here in your green sheet. So a polynomial function is a function that looks something like this. So each of these little pieces are separated by a plus sign, so you have a bunch of different terms being added or subtracted together. And in each of these terms, you have this a part, which is just a number, just some sort of number. That number can have anything being done to it, just some sort of number. And then you have your variable x to some exponent. So some number times your variable x to an exponent. The key for it to be a polynomial function is that all of these exponents have to be positive integers. Okay, they have to be two things. They have to be positive and they have to be integers. So somebody tell me what an integer is. Or give me an example of an integer maybe. So examples of integers would be like 2, 3, 4, 5, 6. They're whole numbers. So basically we're looking at positive whole numbers. And there's another little term we need to know about. It's called the leading coefficient or the leading term. So when we talk about the leading term, we're talking about the piece. So we have all these different pieces being added together. We're talking about the piece that has the x with the biggest exponent, okay? So the x that has the biggest exponent, that together with the number in front of it, all of that is your leading term. The just number in front of it's called your leading coefficient, but we're going to use more of the leading term idea together. So let's do a little bit of practice of recognizing what is and what is not a polynomial function. So which functions are polynomial functions? So if not, we're going to explain why it's not, and if yes, we're going to state its degree. So the degree of a polynomial function is that exponent, that biggest exponent, whatever that biggest exponent is on that one piece, that's the degree. So let's look at that. Oh, that should be a 5, I'm sorry. Negative 3x to the 5th plus the square root of 2x squared plus 5. So first off, is this a polynomial function? Yes or no? Remember, the two things we have to look for a polynomial function is that we have to have all these little pieces being added together, and then the main thing is that the exponents on our variables have to be two things. They have to be positive integers or positive whole numbers. So if you look, the exponent on this x is a 5, so that's good, and the exponent on this x is a 2. That's good. So we meet both of our criteria. So that is yes, it is a polynomial function. And then remember, we want to state the degree. Okay, so the degree is the piece that's got the biggest exponent, okay? Or has to do with the piece that's got the biggest exponent. So this is the piece that's got the biggest exponent, and the degree is actually what that biggest exponent is. So the degree here is 5. Okay, this one, is it a polynomial function? Well, to look at this one, we kind of have a little weird thing going on with the square root of x, okay? Square root of x is a little bit weird because it's not an exponent. But there is a way, if you remember, to rewrite a square root as an exponent. What exponent corresponds to a square root? So a square root can also be thought of as an exponent to the 1/2. So square root of x is the same as x to the 1/2. And I wanted to do that, remember, because to find out if it's a polynomial function, I'm looking at the exponents on my variables. So now, the two things we have to look for are if all of our exponents are positive whole numbers. Are all of my exponents positive whole numbers? Well, 1/2 is not a whole number, so that's not true. So this is no. It's not a polynomial function, and it's because the exponent is not an integer or a whole number, if you want to think about it that way. Last example of this type, h of x equals -3 over x squared plus the square root of 2x to the 5th plus 5. Again, there's kind of a weird thing going on with my variables here. I have a variable in the denominator. What's a way to get my variable out of the denominator? If you remember, it's got something to do with the exponent. So instead of having to write my variable in the denominator, exponents moves to the denominator when they're negative. So if I want to bring it back up, I can make it 3x to the -2, okay? Because it would have gone down because of a negative exponent. So I can just move it back to the top by changing it back to a negative exponent. And I want to do that again because I'm looking at the exponents on my variables. So now looking at the exponents on my variables, do they meet my criteria? No, they do not. And it's because of this exponent right here. It's not a what? Had to be what? Positive and a whole number / integer. And this one is not positive. So looking at the graph of a polynomial function, we can also tell by looking at its graph if it is a polynomial function. So polynomial functions, they have to have degree 2 or higher. Okay, they have to have at least an exponent on there. And they're functions if they are smooth and continuous. So over here on the left, we have some examples of polynomial functions. You'll see they're continuous all the way around. There aren't any breaks in them. And then all my terms are nice and curved. They're not sharp. Over here, these are examples of not polynomial functions, and it's because right here, there's a disconnect in our graph, so it's not continuous. And this one, it's got these sharp corners, so that's not smooth. So, to be a polynomial function, it's got to be smooth and continuous on its graph. Now, there's another really cool thing called end behavior that we can get a lot of information out of about a polynomial function. So the end behavior is what my graph is doing to the far left and the far right. So looking back at like this graph right here, what's it doing as it goes out this way? Well, this one's going up. What's it doing as it's going towards the left? Well, it's going down. So we can figure that out just by looking at the function. And the way we do that is by using the leading coefficient test. And what we use for the leading coefficient test is we look at the term with the highest degree. So we're looking at that leading term we were talking about a minute ago. We're looking at whatever term has the biggest exponent on it. So once we have that term kind of pinned down, let me try and zoom in a little bit, that would be easier. We're looking at this piece right here, and this is the piece that's got the biggest exponent on it. And we look at two things. We look at the number out front, and we look at the exponent. When we look at the number out front, we look at if it's positive or negative, okay? So I want you to think about a quadratic function, okay, an x squared function. Now, if it was just x squared, we've already talked about what it looks like. Its shape looks like, I gotta zoom out now, looks like this kind of curvy thing, right? I think it'd be easier if I just drew it. So if we look at, just think about like a quadratic function. right? It kind of looks like that. And you can see, what is it doing to the right? Well, it's going up, okay, because it's positive. So anytime our number is positive, our end behavior is going to go up to the right, okay? If you think about a negative x squared, negative quadratic, it's going down like that. So what's it doing to the right? It's going down, okay? So if your number out front is positive, it's always going to go up to the right. If your number going down is negative, it's always going to go down to the right, okay? And then we use this exponent up here to figure out what the other side is doing. So we use positive and negative in front to figure out what it's doing on the right, and then we use the exponent to figure out what it's doing on the left side. So we look at even or odd for this exponent. If the exponent is even, okay, then it's doing the same thing on both sides. So again, this is like our x squared. 2 is my exponent. Okay, it's even, they're doing the same thing on both sides. Okay, so if it's even, they're doing the same thing on both sides. If this exponent is odd, then they're opposite in behavior. They're doing opposite things. Okay, so the steps for this, we look at positive or negative. Positive or negative tells us what it's doing on the right, and we can remember that by remembering just our x squared function. And we look at our exponent for even or odd. Even is the same, opposite is odd. So let's do some practice of finding our end behaviors. So use the leading to determine end behavior. Okay, so here's my function. To use the leading coefficient test, I need to find the leading coefficient, or the term that's got the biggest exponent. Okay? So here is my term with the biggest exponent. It's got a 3 on it. This is my leading term. And notice there's not really a number in front of x cubed, but we can just fill in that kind of invisible number with a 1. So that's 1x cubed. And now I look at two things about my leading term. The first thing I look at was what? Well, I look and see if this number out here is positive or negative. So is 1 positive or negative? Well, it's positive. So that tells me what my function is doing on the right. Okay? So if we think about just a regular old quadratic function that's positive in front, what is that doing to the right? Well, it's going up to the right. So positive here tells me that as I go to the right, I'm going up. The next thing I look at is my exponent. And I look at what about my exponent? I'm looking to see if it's even or odd. Okay, so this one is what? It's an odd degree. 3 is odd. So odd means opposite. So that means the left side is doing opposite the right side. So if I'm going up to the right, then the left would be going down. So that's my end behavior. It would be falls to the left and rises to the right. And that's all you do to find the end behavior. Let's do another example of this. This one's going to look a little bit different, but I want to confront it with you, then leave you alone to do it. This one's a little bit different because it doesn't look the same. So then for a polynomial function, you had all these different pieces separated by what? Well, what's separating all these terms? Plus and minus signs. Do I have plus and minus signs separating my different pieces here? No. See, this is being multiplied together right here. Okay? And that's a little bit weird. So let me write a little note. This is not in the right format. Because it's like this being multiplied, it hasn't been multiplied together yet, so I can see my string of different pieces. I can't exactly see what my term with the biggest exponent is, because it's going to get multiplied and it's going to get bigger. So this is not in the right format. So we could multiply this all out. But first off, multiplying that all out is going to be a really big hassle, and I don't need to know all of it because I'm only looking for one piece, right? I'm only looking for the biggest piece. But we just need to know the biggest piece. Or the biggest term. So the way the biggest term is going to be formed, well, that's going to happen when each of the biggest pieces from each thing being multiplied is multiplied together. Does that kind of make sense? Okay, let me write this out a little bit. We just need to know the biggest term, so we can multiply the biggest x term from each piece to find this biggest piece, or find this biggest term, the leading term is the correct word for that. So I just need the leading term. The leading term is the term with the biggest exponent, okay? So if I just need to know the term with the biggest exponent, I'm going to get that by multiplying all the biggest x pieces together. So I kind of want to separate this out a little bit. Here, this negative 4x squared, that's one thing being multiplied together. But then I have this x minus 1 piece how many times? I have it twice because it's x minus 1 squared. So times x minus 1 times x minus 1. So my three things being multiplied together here are negative 4x squared, x minus 1, and x minus 1. Okay? So the leading term is going to come from the biggest x pieces that are multiplied together. So this is one piece altogether, okay? And if you look at it, there's not multiple little pieces inside of it, okay? It's just one thing altogether, okay? So this is one of the things I'm going to multiply because it's all together. But then in this next piece, I have options, okay? I have an x and I have a 1. Well, what's the biggest x piece here? Well, it's going to be the x. Same thing here. I have two different things. I have an x and I have a minus 1. Well, I want to pick the biggest x thing. So that's the x. So we multiply all three of those things together. This is get negative 4x squared times x would be negative 4x to the 4th. And that is my leading term.